Quantum leap forward. Reversing time for particles and its implications. In a monumental stride within quantum physics, scientists have developed a groundbreaking technique to reverse the temporal evolution of quantum particles. This innovation, known as the rewind protocol, allows researchers to revert a quantum system to its previous state without needing to know its prior history or trajectory. This discovery not only reshapes our understanding of time at the subatomic level but also holds transformative potential for quantum computing and fundamental physics research. Quantum mechanics, a realm beyond intuition. Quantum mechanics governs the behavior of particles at the smallest scales, where the rules of classical physics break down. Particles can exist in multiple states simultaneously, superposition, and entangled particles can instantaneously affect each other, regardless of distance, a phenomenon known as quantum entanglement. Quantum teleportation, once a staple of science fiction, is a well-documented process for transferring quantum states across space. Now, researchers have added a new layer to this enigmatic field: the ability to manipulate time itself within quantum systems. This breakthrough doesn't involve time machines in the Hollywood sense, with travelers hopping between eras. Instead, it focuses on controlling the temporal progression of quantum particles, entities so tiny that classical notions of physics barely apply. A team from Austria, led by researchers at the Austrian Academy of Sciences and the University of Vienna, has demonstrated the ability to accelerate, decelerate, or reverse the aging of particles like photons or electrons, effectively turning back their temporal clock. The quantum switch, a control panel for time. At the heart of this discovery lies the quantum switch, a sophisticated tool that functions like a remote control for quantum systems. In classical physics, time unfolds linearly, much like a film playing from start to finish in a theater. Quantum systems, however, offer far greater flexibility, akin to streaming a movie at home, where you can pause, rewind, fast forward, or skip scenes at will. Miguel Navascuez from the Austrian Academy of Sciences described the quantum switch's capabilities vividly. It's like having mastery over time itself. We can rewind to an earlier moment, leap forward several scenes, or pause the progression entirely. Working with physicist Philip Walther from the University of Vienna, Navascuez and their team used photons, particles of light, to test this concept experimentally. In their setup, photons were sent through a system involving precisely engineered crystals and the quantum switch. The researchers guided a photon through a sequence of states, then used the switch to revert it to its initial configuration. This achievement is remarkable because, in quantum mechanics, merely observing a system typically disrupts its state due to the observer effect. The ability to rewind a particle's state without prior knowledge of its history or interactions marks a revolutionary step forward. Example: rewinding a photon's journey. Consider a photon traveling through a series of optical devices, each altering its polarization, a property that describes the orientation of its electromagnetic waves. In a classical system, reversing this journey would require detailed knowledge of every device and interaction. The quantum switch, however, bypasses this need. By manipulating the photon's quantum state through a superposition of possible paths, the researchers restored its original polarization, effectively undoing its journey as if it never occurred. The rewind protocol. Resetting without a roadmap. The rewind protocol is the cornerstone of this breakthrough. It enables any quantum particle, whether a photon, electron, or other qubit, a two-level quantum system, to return to a prior state, even if the experimenter has no information about its initial conditions or the processes it underwent. David Trio, a key contributor from the Austrian team, validated the protocol's effectiveness through both theoretical models and laboratory experiments. This was among the most complex single-photon experiments we've ever conducted, Walther remarked. The results were striking. The photon consistently returned to its original state, akin to rewinding a video without ever viewing its contents. This process is not only precise but also universal, applicable to any qubit-based system. Beyond rewinding, the team demonstrated the ability to fast-forward time. Navascuez explained, to age a quantum system by a decade in just 1 year, you need to borrow the additional 9 years from somewhere else. In one experiment, the researchers used 10 identical quantum systems. By extracting 1 year of aging from each of the first 9 systems, they transferred those years to the 10th, causing it to age 10 years in a single year's time. Example: fast-forwarding quantum aging. Imagine a quantum system representing a simplified model of a radioactive atom, where aging corresponds to the decay of its quantum state. By coupling this system with 9 others and using the quantum switch to redistribute temporal evolution, the researchers effectively accelerated the decay of one system while preserving the others. This controlled manipulation of time could have applications in simulating complex quantum processes, such as chemical reactions or material degradation, in a fraction of the usual time. Practical applications: enhancing quantum computing. While the idea of reversing time for a human or undoing life's mistakes remains firmly in the realm of science fiction, due to the immense complexity and information content of macroscopic systems, this discovery has profound implications for quantum technology. Quantum computers, which store and process information using delicate quantum states, are highly susceptible to errors caused by environmental noise or imperfect operations. The rewind protocol offers a way to correct these errors by resetting a quantum system to a previous, error-free state. We're confident this has immediate technological applications, Walther stated. For example, a rewind protocol could reverse unwanted errors or developments in quantum processors, saving computational resources and improving reliability. The team also envisions extending the protocol to systems beyond photons, such as superconducting qubits or trapped ions, and scaling it to more complex architectures. Potential use case: error correction in quantum computing. In a quantum computer, a qubit might inadvertently flip from one state to another due to external interference, such as electromagnetic radiation. Traditionally, correcting such errors requires intricate error correction codes and significant computational overhead. The rewind protocol, however, could reset the qubit to its pre-error state without needing to diagnose the specific error, streamlining the process and enhancing the efficiency of quantum algorithms. Overcoming the arrow of time. Classical physics is governed by the arrow of time, a concept articulated by astronomer Arthur Eddington, which aligns with the second law of thermodynamics. This law states that systems naturally progress toward greater disorder, entropy. However, at the quantum level, this rule is less absolute, as small systems can exhibit reversible behaviors. In classical systems, techniques like phase conjugation can reverse certain processes, such as light waves in optics. In quantum mechanics, however, random noise often disrupts such reversals. Previous attempts at quantum time reversal were limited, requiring either detailed knowledge of the system's state or slow, probabilistic procedures. The new rewind protocol overcomes these barriers, offering a high success rate, over 95% in experiments, real-time operation, and applicability to any qubit system. For instance, rewinding a quantum system by 5 minutes takes exactly 5 minutes, making it practical for real-world applications. The role of quantum operators. The protocol leverages a fundamental property of quantum mechanics, the non-commutative nature of quantum operators. Unlike classical mathematics, where the order of operations doesn't always matter, e.g., 2 plus 3 equals 3 plus 2, quantum operations are order-dependent. This property allows the researchers to create a superposition of multiple timelines, each representing a slightly different evolution of the quantum system influenced by known physical interactions. By carefully interfering these timelines using the quantum switch, the team guided the particle back to its original state, regardless of the specific path it took. If errors occurred, they employed quantum error correction to boost the success rate, ensuring robust performance. Technical setup: manipulating photons. The experimental setup used optical components, such as half and quarter wave plates, to manipulate the polarization of photons, creating different Hamiltonians, mathematical descriptions of how a quantum system evolves over time. Fast optical switches, combined with the quantum switch, mixed these timelines to achieve the rewind effect. For example, a photon might pass through a series of wave plates that rotate its polarization, then be reverted to its initial polarization state by interfering the timelines in a controlled manner. Beyond the lab, broader implications. The team's experiments achieved a rewind accuracy exceeding 95% across various quantum processes, demonstrating the protocol's reliability. This precision opens doors to practical applications, from improving quantum computers to exploring fundamental questions about the nature of time. For instance, the rewind protocol could enhance quantum simulation, where researchers use quantum systems to model complex phenomena, such as protein folding or quantum phase transitions. By reversing unwanted changes, scientists could refine simulations with greater accuracy. Additionally, the protocol offers insights into the nature of time in quantum mechanics, potentially bridging gaps between quantum theory and general relativity, where time behaves differently. Navascues cautions that applying this to macroscopic systems, like a human, is theoretically possible but practically infeasible. If we could isolate a person in a box with no external influences, rewinding their state might be possible, he said. But with current protocols, the probability of success would be vanishingly small, and it would take millions of years to process even a second of their life. Future directions and related research. The Austrian team's work builds on earlier studies of quantum time reversal. For example, previous experiments, such as those by the University of Queensland in 2019, simulated time reversal in simple quantum systems but required precise knowledge of the system's state. Other approaches, like those explored at MIT, used complex quantum circuits that were slow and probabilistic. The rewind protocol's ability to operate without prior knowledge and in real time sets it apart as a significant advancement. Looking ahead, the researchers plan to extend the protocol to more complex systems, such as multi-qubit setups or non-optical platforms like superconducting circuits. They also aim to integrate it with existing quantum error correction techniques to create more robust quantum processors. Beyond computing, the protocol could find applications in quantum cryptography, where precise control over quantum states is critical, or in quantum sensing, where time manipulation could enhance measurement precision. Connection to other quantum phenomena. The rewind protocol shares conceptual similarities with quantum teleportation and entanglement swapping. In teleportation, a quantum state is transferred between particles using entanglement, while the rewind protocol transfers a system back to a prior state using temporal superpositions. Both processes exploit the non-local and non-classical nature of quantum mechanics, highlighting the field's potential to redefine our understanding of physical reality. Conclusion: a new era for quantum control. This breakthrough in quantum time reversal is more than a theoretical curiosity, it's a practical tool with far-reaching implications. By offering unprecedented control over quantum systems, the rewind protocol could pave the way for more reliable quantum computers, advanced simulations, and deeper insights into the fundamental nature of time. While rewinding a human's life remains a distant dream, the ability to manipulate time at the quantum level brings us closer to mastering the subatomic world.